I'd like to first thank the organizers for organizing this wonderful workshop. I really learned a lot over the past couple days. So today I'd like to talk about some recent work that we carried out at my group at the University of Waterloo. I'll get to talk around what this is in a moment. But what I would like to do is I would like to actually carry forward, I guess, the theme of today of quantum optics and trying to push the complexity frontier of atom-light interaction. So perhaps one way of trying to enrich the complexity of these kind of quantum optical phenomena is to really engineer the dielectric at which the atoms are being coupled to. So you can really think about engineering the quantum electromagnetic vacuum of the dielectric with some kind of engineered structure. Take it perhaps a photonic crystal waveguide that have some exotic single particle property and dispersively couple an atom array to this waveguide so that, by adiabatically eliminating this QED modes, what you end up is, somehow some non-trivial interactions between these atoms. So in some sense, you can perhaps use the atom-light interaction to enrich the complexity of initially a non-interacting spin system. So really, this is the perspective of waveguide QED that we have heard about before, where this kind of engineered kinetics of the photon bath give rise to unconventional interactions in this kind of atom array. But perhaps in some sense, this setting is a little bit limited. If you think about what is the mediator that is causing interactions between these atomic dipoles, and the reason is when you think about effectively photons being populated in the dielectric, it's really almost the same as a free space photon excitation. Like there's no intrinsic interaction between the photons to begin with. If you want to, for instance, generate some local symmetry in this sort of setting. So over the past 6 years or so, what we have began is this conceptual framework of many-body quantum electrodynamics. I'll get to define that a little bit more concretely in a moment. And the way to think about this is, instead of thinking about the dielectric substrate that is mediating interaction, you think about this gain medium or a many-body system that is strongly interacting as a quantum substrate and couple it to the cavity field. And what one would kind of naively anticipate is in this kind of more or less quantum substrate, you have basically the ground state or the vacuum state of some sort of strongly coupled quantum field theory, and you have emergent excitations that perhaps might couple to the light field and give rise to novel phenomena in quantum optics. So that is kind of like the high-level perspective that I'd like to take in talking about some of the experiments that I'll discuss in a moment. So one example that I'd like to talk about is perhaps a quasi-particle that could be, or perhaps a kind of a many-body system that is interesting but yet classical, but could be promoted by coupling to the vacuum fluctuation of the cavity. And in this setting, what I'll talk about in a moment is we can actually generate interesting quasi-particles in this kind of hybridized systems known as bosons that are kind of famously known as sort of dark matters of spin liquids because they don't carry any energy or spins in the charge or spin in the system. So for those of you who are much more familiar with many-body physics than I am, you can kind of see this connection between extrinsic and intrinsic topological order in the way that I was describing in this slide. So let's first talk about what gain medium that we're coupling to this cavity, and what we're going to be doing is basically borrow the technology that was developed over the past many years on Rydberg tweezer arrays, and use the interatomic interaction, essentially the Ising model, the van der Waals interaction between these atoms, to basically provide some local constraints in this gain medium. So the setting that I'm talking about, to be more concrete, a strongly coupled many-body QED is defined as staying in the single photon, single atom limit of strong coupling regime of standard cavity QED. Basically, you have the atom-light interaction G naught to dominate over the loss rate through the cavity, and also the transverse decay rate, the spontaneous emission rate of these atoms inside of this many-body system. But what you would like to have, in addition to that, is actually have a local constraint where the interatomic interaction dominates over even a strongly coupled atom cavity coupling rate. And you can, in some sense, see that at least among the toolboxes that we have with neutral atoms, Rydberg atom is really the only way that we can dominate over this kind of atom cavity, vacuum rapid splitting of tens of megahertz. So I like.
Who's mediating the interaction? The Rydbergs per se or the cavity field?
Sorry, I couldn't.
Who is mediating the spin interactions? Are the Rydberg?
It's fundamentally the Rydberg, but then I'll talk about the atom cavity interaction inducing some interesting dynamics that are constrained within the subspace defined by these Rydberg interactions. Yeah, so the cavity does play a role, but I'll get to that in a moment. So I'd like to talk about, we actually heard a very nice talk yesterday on Rydberg spin ice, but I'd like to talk about this spin ice as a kind of a proxy to of an interesting quantum material that could be promoted into something yet even more interesting. And I'd like to talk about, in particular, a 3D pyrochlore lattice of what people study in these kind of rare earth magnets in the condensed matter community. And what this is basically, this pyrochlore lattice is basically consists of sublattice of tetrahedrals. And tetrahedrals are three-dimensional triangles. It's actually maximally frustrated in the system. And as we heard yesterday, it actually has a very interesting property where if you have this ice Hamiltonian, if you have Rydberg atoms that are causing these antiferromagnetic interactions, what you find is in the low energy sector is actually basically local conservation rules that is known as ice rules. So you basically have two spins pointing in, two spins pointing out. And as we heard yesterday, there is a very delicate connection to imposing a Gauss's law in this kind of system. So the other way to kind of think about this is, well, you can actually rearrange this Ising interaction in terms of essentially a Lagrange constraint. And what you find, well, if I add this constant Q, you can actually find that by tuning this Q, you can go into different charge sectors inside of this kind of ice material. So I found it kind of interesting to kind of make this connection because to the electrostatics, because actually if you take two tetrahedrals that is actually sharing a single spin that were initially prepared into two spin pointing in, two spin pointing out in both of these sublattices, and actually just flip this one spin, you can actually find that you are creating two gauge charges in the system. And these electric charges are actually being mediated. You can think of this single spin as a coarse-grained electric field that is basically mediating the Coulomb potential in these kind of gauge charges. So these are kind of also known as monopoles in this kind of spin ice context. So of course, in 3D, as you'll see in a moment, is quite difficult. We don't know yet how to do this in the lab. So what we do is we actually project this tetrahedral into a square ice. And as we have heard yesterday, there is some complications of how you can engineer the interaction so that it's sort of all too well connected within these kind of small ice cells. And I'll get to talk about that, how we overcome this challenge. So one way of actually promoting this square ice into something more perhaps quantum mechanical is to add some form of quantum fluctuation on top of the background of these ice constraints. And as we have learned yesterday, these quantum fluctuations can actually give rise to plaquette dynamics or ring exchange dynamics, where if you think about, let's say, kind of exchanging these two spins, you find that you're creating two electric charges in the system that are extremely high energy, and there's a virtual, and therefore there's a virtual process where you must actually flip the other spin, and you end up with this kind of four-body term in this kind of effective Hamiltonian. So there's this kind of nice connection to doing this, at least in 3D, that you can actually end up with basically a QED like Hamiltonian in terms of like lattice gauge theory. And in the traditional context of 3D particle lattice, people have studied theoretically and experimentally possible gapless spin liquid phases in this kind of materials. So the question is, can we actually also get a spin liquid in this kind of two-dimensional setting, a U1 spin liquid? And the answer is negative. That Polyakov showed a long time ago that there are basically instantones in these systems that lead to a symmetry breaking, and what you end up is typically these kind of plaquette valence bond solids in the system. In our experiment, what we do, instead of putting this kind of nearest neighbor quantum fluctuation, is actually couple this Rydberg ice that is otherwise classical and extensive into the infinite range vacuum of the cavity mode. And I'd like to emphasize that this situation is actually fundamentally different from what I just talked about in 2 dimensions, in the sense that if you ask what is the physical dimension of the system, you have local constraints that are in 2 dimensions, but then we're coupling this to the non-local QED vacuum, which is a 0-dimensional system. So it's really a hybrid physical dimension, and it still kind of raises the question, what is the kind of phase diagram of this kind of atom-light system?
Sorry, I have a question.
Yeah.
But don't you also get long-range ZZ interactions when you put the atoms in a cavity like this?
From the yes, we do. Yeah, but that's actually going to be very small compared to the native Rydberg interactions, because we're in this kind of strong constraint regime.
But is it also small with respect to the effective coupling that you get in perturbation theory for the plaquette, or it is not small with respect to that?
It is small with respect to that.
Okay.
Yeah, but that's a good question.
So maybe this is related to my previous question. So if you mediate long-range interaction with the photons, basically properties will be all-to-all. So it will be connected to collective magnetization, right? It will not be connected to finite momentum excitation.
If there was no local constraint, you would be right. But
But
because of the local constraint, you get some locality. Yeah. So you cannot like simply flip one spin and another spin over there, because you would create 2 long-range gauge charges that you cannot annihilate otherwise.
You will discuss this later?
Probably not, but we can talk about it.
Because I'm not
Afterwards.
sure immediately. I agree, but maybe I'm missing something.
Yeah, it's really because it's like these ice cells are corner sharing, and it's not very easy to, like, the only way to kind of unravel this is to have like a kind of an n-body ring exchange interaction, and that's a very high energy
But this should have nothing to do with the linear coupling between light and matter. Let's say, you have a Travis couplings, Travis Cummings coupling.
Yeah,
right?
yeah.
This will mediate something like S plus S minus collective, and doesn't know what, I mean.
No, but you cannot do it because you are violating the gauge constraint twice.
No, but you can put it in the Hamiltonian.
You will, no, but
You can. Yeah, you can put it in the.
Jamir says it should be total S plus times total S minus.
Exactly.
And just solve the Hamiltonian that has this term and has a constraint.
But isn't it like this in the previous? I know. Okay.
No, it's different.
Ah.
Well, at least we didn't see this term.
That's it. That's the question.
Yeah, we can talk about this further. Yeah, but kind of a proximal situation to this kind of Travis-Cummings or infinite range situation is if you imagine that you have sort of a localized photons that is decaying polynomially with maybe a exponent of alpha, and ask the question about if you have kind of long range quantum fluctuation that is dressing this Rydberg ice, what happens in the setting. And this was actually kind of examined before, where you can actually interpret these kinds of dimer moves where dimers are sitting on diagonals of these ice cells as Higgs fields that they can condense and lead to a Z2 deconfined spin liquid in the setting. So the hope is maybe this physics does carry over, and we can generate a quantum spin liquid in the system. So I'll show you the theoretical phase diagram in a moment, but what we're going to be seeing are basically kind of two types of exotic states. One is a valence bond solid, which is kind of like a crystal of dimers, and then you also have these resonating valence bond states, which is basically a kind of a macroscopic superposition of different dimer coverings in the system. And one of the hallmark of these deconfined spin liquids is that you have exotic excitations where you have these kind of vibrating loops that basically screen the interaction, the confining potential between these anyons, and they're actually deconfined in this kind of spin liquid. So this is a infinite size matrix product state simulation for two cases where you have 1 over r to the 6 type of quantum fluctuation, 1 over r to the 2 of quantum fluctuation, and what you find as a function of different electric charge sector and constraint is there is a finite region at which a Z2 spin liquid could be stabilized. This is kind of like the theoretical phase diagram, and you can also look at the kind of the plaquette or the kind of microscopic Wilson loops in the setting, and you can actually categorize different valence bond solids in the system and two types of potential spin liquid states that might be stabilized in this setting. Actually, how am I doing with time?
7.
Oh, okay, yeah. So, yeah. Okay, so yeah, I want to talk about the experiment. So, this is the hard part. So this is our many-body QED platform. It's a fairly good cavity system, has an optical finesse of 500,000, a length of 500 micron, and we're in the strong coupling regime with these parameters, and you can see that this G0 13 megahertz is kind of reasonably small, so that we can actually have Rydberg interactions that dominate over this atom cavity coupling rate. And I won't go into too much detail, but on this side we have a high resolution microscope where we can engineer these tweezer array and kind of move atoms within this cavity. And what you see on these kind of gold electrodes are basically RF dressing fields that we put into the system to basically reduce long range Ising constraint that would cause trouble if we didn't do this in terms of like imposing a good ice constraint in the system. Yeah, so long story short, we can kind of do these tweezer arrays. And it's a little bit more complicated in the lab, but okay. So we initially prepare these square ice, and the way that we're going to be engineering these ice rules is by embedding, basically separating the system into these kind of green balls, which are the system atoms, and then we have these reservoir atoms that are effectively mediating interaction between these 4 atoms. So this is how we engineer these ice constraints in the system, and we couple to the cavity field to basically, add quantum fluctuation on top of this ice background.
So I have a question about this. What is the role of residual interaction between these orange atoms that you use to mediate the interactions?
Sorry, I couldn't quite understand.
What is the residual effect of the fact that you have finite interactions between the orange atoms?
Oh, orange atoms.
Yeah, the reservoirs.
That's so these atoms, although you cannot really see, are actually positioned ever so slightly so that they're actually not positioned at the antinode of the cavity. So there's also the question about how do we kind of position even the global kind of phase of this lattice to the cavity field. And yeah, there's kind of whole technical detail that, yeah, I'm skipping through. But yeah, we can talk about that.
Just to understand this, IJ means what? It's just only green atoms, or does it include orange?
Oh yeah, these are basically the system Hamiltonian. So it's only the system atoms. Yeah, so it's after adiabatically eliminating these reservoir atoms, and we're doing some kind of Rabi oscillations for the.
What's the distance between the atoms here?
Sorry?
The physical distance between the atoms compared to the wavelength of the cavity?
It's about 4.8 micron, this lattice constant. Yeah.
Another technical question. Do I understand correctly that in your tweezer, your atoms are not in the ground state? They're actually in some excited state. So parameters actually sort of fluctuating of the order of 10% or so.
So these atoms are actually in the ground state?
Of this tweezer.
Oh, the motional ground state.
Motional ground state.
Oh, no, they're not. Yeah.
Exactly, but that's so. Am I correct that then in these parameters of your Hamiltonian, I actually random by something like 10%, because atoms are not in the ground state.
What do you mean by 10%?
Oh, because the distance changes, right? So if the distance changes, therefore, your interaction constant.
Yeah, that's right. Yeah, so there's a bit of, kind of noise in some sense.
I'm just curious about the number. Other experiments I've seen, it was of the order of like 10%. So I'm curious, what is the number for you?
You mean the 10% in the motional ground state?
Or if I can work fluctuations in the motional state into uncertainty of effective spin Hamiltonian, it was around 10%.
Yeah, that might very well be. Actually, we didn't look into this. Yeah, but yeah, I'll get back to you. Yeah.
Sorry, maybe because everybody was asking now. That's exactly the point I was mentioning before. So if you eliminate the photon, you are going to use a collective S plus S minus interaction, which of course is going to beat and frustrate with the Rydberg, no discussion. But this doesn't give quantum fluctuations because it's a collective spin, right? It's a collective spin exchange. So any fluctuation will be suppressed in 1 over n, and I assume you have n that is enormous. So that was the part I was a little bit confused about. I don't know that much about lattice gauge theories, but I understood from your introduction that you needed some sizable quantum fluctuations to lift degeneracy. So
I think what you're saying is like in the limit where delta C is like the largest in the game, then you would be right. But then this delta C is certainly larger than this, but it's actually smaller than this. So it's actually not very clear you can do a perturbation that just ends up with the S plus S minus.
I see. So you don't work with completely further-tuned photons.
Yeah. But I don't think that actually changes the physics that I'll talk about like in a moment. I don't think it would. Yeah. Oop. Since I'm running quite a bit late, I'll just skip some slides. And so one of the measurements that we have in the setting is we can basically make fluorescence measurement, site results fluorescence measurement, both in the Z basis and also in the X basis. We can use some Rydberg pulses to basically rotate the spin vector pi over 2. So the first kind of sense that we have, like a frustrated system, is we can actually try to look at each snapshots of the quasi-adiabatically prepared state. And what we find, like for instance in this image, is that where the I cells are residing, you always have like 2 spins pointing up, 2 spins pointing down. So in the system, you can actually find very little defects in the system. And time to time, you do see these defects, which are basically thermal spin-ons in the system. And we can actually repeat this measurement about 2,000 times. You find some amount of defects, and mostly 2 spins pointing in, 2 spins pointing out. So really in this kind of zero electric charge sector of this kind of ice Hamiltonian. And the other kind of interesting thing that I would like to highlight is that among these 2,000 images, there's actually no single 2 images that are actually overlapping. So maybe that's some kind of indication that the system is indeed extensive. So what we do is we actually kind of lay these fluorescence images in this kind of pretty 3D cartoons where kind of these white atoms are spin up, black are spin down, or maybe the other way around. So then what we can do is we can actually collect a bunch of these images and then try to calculate the Wilson loops in the system. So we're talking about 2 types of Wilson loop. One is basically kind of like X, 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 Z, 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 Z. And in both cases, what we find is for these kind of microscopic Wilson loops is actually quite far away from being 0. So you can actually see that for both of these measurements, for instance, the Z Wilson loop is very close to 1 in the system. Okay, so this is another kind of image of these kind of accumulated fluorescence images, and kind of looking at what is the Q in the system, and you can find like where Q equals 0, 2, and 4 as we kind of vary the constraint in the system. So to kind of further show whether this is really a spin liquid, we can kind of go one step further and look at the correlations built between the Wilson loops. And for what we think is the Z2 spin liquid, we don't really find kind of long-range order in these kind of mQED operators. And what we think is the Valence bond solid, there seems to be kind of a longer decaying tail in this at the Q equal 2 sector. So we can start drawing a little bit larger Wilson loops and then basically try to detect deconfinement. And we heard yesterday that there are some perhaps problems with this form of analysis. But yet what we do is we try to measure the string tension by drawing larger Wilson loops and kind of making these measurements. And what we find is well, this is again these microscopic Wilson loops. We can see there what we think is the Z2 spin liquid valence bond, this kind of all spin up ordering. And what we find is there's a finite region where both the Z and the X operators are actually kind of non-negligible, and we can characterize from these kind of enlarged Wilson loops these string tensions. And the string tension, you can find that as we kind of cross from the spin liquid to the valence bond, there is kind of like a diverging tensions that you can detect through these measurements. I guess I'm yeah. Okay. So yeah. So this is another kind of cut of the phase diagram, and I'll just finally talk about this kind of half loops that we heard yesterday. And in this kind of spin liquid, we do find a vanishing Fredenhagen-Markov order parameter in real space. And then it goes back up in this kind of symmetry breaking phase. Finally, I'll just talk about quasi-particles that we can probe. So the way that we're doing this experiment is we're basically looking at the photons leaking out and basically putting on a spectrum analyzer and trying to detect the beat note frequency of the light field leaking out. And this indicates depending on how we drive the system, it populates spin-ons or bosons in the system, and we can use this beat node to basically characterize the dynamical structure factor of these quasi-particles. And instead of like globally driving the system, we can actually locally address, let's say, 4 atoms to look at not this kind of more like G1 type measurement, but also like higher order correlations. And when you look at G2, there's a component at which goes something like sigma plus, sigma minus, sigma plus, sigma minus, which is basically this ring exchange term. And from the change of these G2 as we create a boson in the system, we can actually detect this kind of mutual phase of braiding anyons in the system. And we find it's, kind of, non-zero, in this setting. So I guess I'm really out of time. So yeah. So oops. Yeah, so I'll be happy to answer any questions, and we can also chat during lunch if you have any further questions.